Dear viewers, welcome to the UGC lecture series in biophysics. Today we are going to deal with an important topic called hand propagation by direct methods. In the absence of computers in the 1940s or 50s, how scientists solved the molecular structures, how did they get the phase estimation and so on using direct methods. So, I will explain you in detail whatever the hardships they faced, and at the end I am going to give you a list of reflections which you can yourself do it as an exercise, so that you can feel how difficult it was for those people in earlier time to face the reflections. Now, here the important thing we are going to consider is a centrosymmetry case. We have already defined a centrosymmetry case. For every atom j in positions x j, y j, z j, you can find an identical atom. Suppose you have a carbon atom at position x 1, y 1, z 1, there should be another carbon atom maybe again at minus x 1, minus y 1, minus z 1. If there is a nitrogen atom at say position x 4, y 4, z 4, there should be another nitrogen atom at minus x 4, minus y 4, minus z 4. For every atom at a particular position, in the inverted position same atom should come, that is known as centrosymmetry case. In general, suppose your structure consists of n atoms, out of which in the unit cell n by 2 atom will be having some positions, the remaining n by 2 will be the inverse of their positions. So, this is known as centrosymmetric structure. Why we are specific about the centrosymmetric in the case of phase determination is that the phase problem or overcoming the unavailability or non availability of phases becomes easier in the case of centrosymmetric case, because in centrosymmetric phases can have only two choices, either 0 or pi. So, whenever they have 0 or pi, structure factor of a reflection already we have seen f of h equals modulus f h e power I phi h. When you substitute this phi h as 0 or pi, your f of h becomes plus or minus modulus f of h. So, in case of centrosymmetric, you can talk either in terms of phases 0 or pi, or in terms of the algebraic signs plus or minus to be assigned to the amplitude of structure factor, which you get from experimental intensities. David Sayer in the year 1952 proposed an equation for obtaining the algebraic sign of a reflection h. H means a set of 3 indices h k l, maybe h 1 k 1 l 1, h 2 k 2 l 2, the h 3 k 3 l 3, and these h's, k's, l's can be either 0, positive or negative integer. Okay. Now, if you know the signs of other two reflections k and l such that this h plus k plus l is 0, I already explained you what do you mean by h plus k plus l equal to 0. Each is a set of 3 reflections h 1 k 1 l 1, h 2 k 2 l 2, h 3 k 3 l 3. By this I mean 3 equations, h 1 plus h 2 plus h 3 will be 0, k 1 plus k 2 plus k 3 will be 0, l 1 plus l 2 plus l 3 should be 0. All the 3 should be satisfied, then only it is called h plus k plus l equal to 0. Here all the atoms are assumed by Dr. David Sayer to be identical, and the hypothetical structure is called a squared structure. Why is it called hypothetical? When you talk about a molecule, molecular structure is there that corresponds to some sort of electron density, but he assumes that this structure, which is called hypothetical structure, has square of the density, right. That is called, this hypothetical structure is called a squared structure, where all the electron densities are squared. If it is the ordinary structure, we talk about atomic scattering factor little f j. Since in a square structure, you cannot have atomic scattering factor little f, but some other quantity is there. Let us see what is that later. If the atoms are considered sufficiently far apart, then automatically their electron density do not overlap to an appreciable extent, and the square structure also consists of equal spherically symmetrical atoms whose scattering factors may be calculated exactly as a function of your h, because already we know same thing. Peak position will be the same in the squared structure as that of the other structure. Suppose you have a structure contributing to electron density. Okay. So, electron density maximum are atomic positions. Now, if you consider square of the density, that peak position will be same, only thing is the density value will be square, that is all. So, do not have any confusion. Now, the equation 1 is known as Sayer's equation. The structure factor F h is related in terms of two other structure factors k and h minus k by this factor 1 by V multiplied by little f by gamma. What is the little f? This corresponds to atomic scattering factors of atom leading to rho of our electron density, and this gamma is like a scattering factor corresponding to the electron density rho square r, this is called square density. V is as usual same definition, volume of the unit cell. Here remember 1 by V is a factor multiplied by little f over gamma. Starting from this equation 1, they have derived a simple equation, I am not going into details. The product of three signs H reflection, K reflection and H plus K reflection is probably negative, not nearly, probably positive, because the probability relation nothing is exact. So, three reflections are there, H reflection, K reflection. If you add H and K, we get new reflection called H plus K. Then the product of the signs of these three reflections should be positive, right. That is what I mean. S of H means algebraic sign. It may be because centrosymmetric, no, it can be either plus sign or minus sign. Correspondingly, the phases can be either 0 or pi of reflection H. Okay. Again, as per probability theory, in direct methods, larger the structure factor amplitudes mod E h, mod E k and mod E h plus k of these three reflections H, k and H plus k, larger will be the probability for the product of the three signs to be positive. Using the above equation and knowing the signs of the reflections H and k, assuming two signs to be known, I can find the sign of the third reflection, which is obtained by simply adding H and k, right. Now, as I told you, in centrosymmetric case, phase problem gets simplified, because the phase of a reflection can just take two values 0 or pi. And since we know that structure factor is a complex quantity, it can be represented as an amplitude mod h, which is obtainable from the square root of intensities from diffraction experiment multiplied by exponent e power I phi h. This phi h is the phase which is unknown from experiment. Now, okay. When you substitute for this phi h 0, e power 0, anything power 0 is 1. So, we get f of h simply mod f h or plus mod f h, both are same. When you substitute your phi h as pi, other possibility, e power I pi you have, e power I pi is cos pi plus I sin pi, sin 180 is 0, cos pi we have minus value, minus 1. Therefore, we have only two choices in centrosymmetric case for the phases, namely 0 or pi, and correspondingly f of h will be plus mod f h or minus mod f h. So, that is what we can also define phase problem in centrosymmetric case as assigning of algebraic signs plus or minus to the structure factor amplitudes obtained from experimental intensities. Okay. Now, the reflections H and K are chosen from the origin defining reflections. So, this I will give you a separate lecture, how to choose origin defining reflection. Direct methods your phasing depends on origin defining reflection, because you use them and assume their phases or signs to be known. Phases means 0 or pi, or the signs plus or minus. Of course, for enhancement of your discrimination, you take one more reflection. That is what I told you one of the presentation. Usually we take your 5 reflections, 4 reflections for origin fixing and 1 is for enhancement of fixation, and you know the phases or symbols are all these 5. Depending upon these 2 power 5, 32 sets, each set you can have the rest of the 395 reflections if you start with 400 reflections. Okay. Now, strong reflections, Sayer equation can also be written as sin of h multiplied by sin of k is nearly equal to sin of h plus k, because you know that this algebraic sign can have only 2 choices, plus or minus. When same reflection sign is multiplied again, whether it is plus or minus, the product will be having plus sign only. I will just give you a simple example. Previously I shown that S of h multiplied by S of k multiplied by S of h plus k is nearly positive. Now, I am rewriting Sayer equation this way. There is nothing wrong, same. If you multiply both sides by sin of h plus k, here we get previous Sayer equation S of h into S of k into sin of h plus k equals sin of h plus k multiplied by sin of h plus k. Now, sin of h plus k, it is can be either positive or negative. In both the cases, sin of h plus k multiplied by sin of h k will be plus only. So, we get back the same old Sayer equation, sin of h multiplied by sin of k multiplied by sin of h plus k is nearly positive. So, it is left to you only, just understand, that is all. This is also Sayer's equation, previous one also Sayer's equation. Now, in this equation, suppose this sin of h reflection is negative and this is positive, then this has to be negative, that is all. So, knowing the sign of two reflections, I can get the sign of the third reflection, that is it, that is called Sayer equation. Okay. This is for centrosymmetry. Suppose it is non-centrosymmetric case, we have seen that in this case phase can be anywhere 0 to 2 pi, any value 0 to 2 pi. Now, even though the Sayer's equation is not strictly valid for unequal atoms, the criteria that the atoms in a structure are identical, symmetrical and do not overlap in space will lead to diffraction amplitudes and phases which are connected by exact equations. Now, from the Sayer's equation 1, we can get an equation in terms of phases, namely phi of h plus phi of k plus phi of minus h minus k is nearly equal to 0, right. Now, whenever this nominal structure corresponding to this E h, that is mod E h and mod E k are larger, then your phi of minus h minus k will be nearly equal to phi of h plus k, and this equation can also be rewritten this way: phi of h plus phi of k will be nearly equal to phi of h plus k. So, in centrosymmetry we have seen sin of h times sin of k will be nearly sin of h plus k. If it is phase, you have to add the phases of h and k to get the phase of h plus k, non centrosymmetric. If it is centrosymmetric, multiply the signs of h and k reflection to get the sign of h plus k, that is all, very simple. So, the above equation is used. So, Sayer's equation, we are given two equations, one is for the centrosymmetric, namely sin of h multiplied by sin of k equals sin of h plus k, centrosymmetric. Knowing the signs of two reflections, multiply by the sign to get the new sign for the new reflection h plus k. Now, we are given another equation, knowing the sign of h reflection and k reflection, add the phases to get the phases of the new reflection, that is all. Now, the second equation is used in the case of non-centrosymmetric case, as you know. This phi of h and phi of k are known as they are usually selected from the origin depending reflections, and knowing these two phases, phases of the third reflection h plus k can be found. So, let us take an example. If phi of h is pi, then phi of k is 0, then phi of h plus phi of k is pi plus 0 pi. So, this will be the phase of the new reflection h plus k. Suppose phi of h is pi, phi of k is pi, then phi of h plus k will be this place plus this pi plus pi 2 pi, which is equal to 0. So, this is how we are going to do. So, you can do the exercise. The wife of the Nobel laureate Jerome Karl, Isabella Karl, she solved some structures using direct methods and she has given a tutorial. Whenever somebody attends the direct method lecture in Iriche, so you will be asked to do the tutorial in direct methods. So, let us see what do you mean by hand propagation of sign relationship in the case of centrosymmetric. So, this table lists the statistic for a structure she named as Jamine. Theoretically, there is a distribution for centrosymmetric structure and non-centrosymmetric structure. If you take average E or average of mod E square minus 1 and average of mod E square, right. There are three statistics, but which statistic is one? Why are we using statistic? you have experimental values. Suppose you have 500 reflections, for every 500 reflection you take the E value, add it, divided by 500, that is known as average of mod E. Then square each E value, subtract 1. So, that may be positive or negative, take modulus, then divided by 500 and that is this value. Then just square it and add it, divided by 500. So, this is the 3 types of averages. If you see here, these are the experimental values they obtained for these 3 types of averages for the structure germane. But theoretically, these statistics for centrosymmetric and non-centrosymmetric are given by Professor A.J.C. Wilson. He is considered the father of crystallography statistics. If you see here, you have to see out of the 3 which is the best statistic. We know the structure is centrosymmetric. But look at the difference between theoretical statistics, centrosymmetric and non-centrosymmetric. The difference is only 0.79, 0.88, very marginal, 0.09. But here is a little bit more. Here it is same. Because by this statistic, we cannot say whether it is centrosymmetric structure or non-centrosymmetric structure, because both the cases mod E square equal to 1. So, this is not a good statistic. Now, if here you see this statistic, centrosymmetric non-centrosymmetric difference is very marginal, but if you use this statistic, the difference is 0.73, 0.96. No, so we have roughly about 0.23 difference is there. So, this is considered as the best statistic, and Professor George Sheldrick in his program Shellax uses only this as the best statistic. Now, experimental values for these 3 statistics are given for germane. If you just see these 3 values, this is 0.728, this is 0.083. This value 0.083, good statistic, is very close to centrosymmetric value theoretical distribution than to non-centrosymmetric. So, now I say this structure is centrosymmetric, because theoretical values of centrosymmetric matches with the experimental statistic. So, this is how theoretically you have to justify whether it is centrosymmetric or non-centrosymmetric if you have some confusion. Next, this we are going to have a separate lecture series, how to choose origin defining reflections and how to assign algebraic signs or phases. So, this is a separate topic. Now, let us see here table 2. Already we have seen that centrosymmetric cases phase problem is simpler, phases can have only 2 choices 0 or pi, and accordingly the sign of the reflection will be either plus or minus. Now, table 2 lists what are all the reflections selected for hand propagation. Hand propagation means you select a small set of reflections, say 3 plus 5, 8 reflections I am choosing, and for 3 reflections, because centrosymmetric, no, I am assuming the phases to be plus, and these reflections are supposed to be very strong E values, because only strong E values give very reliable probabilistic distribution with lesser variance and better estimate. That is why you choose reflections having large E values to generate the triplets. Okay, now 3 are given, signs plus. The other 5 reflections I am putting symbols. So, this is sometimes called symbolic addition procedure, because using symbols. This A can be plus or minus, I do not know, B can be plus or minus, C can be plus or minus, D can be plus or minus, E can be plus or minus. So, here ambiguity is there, but here I assumed only single value plus plus plus. Okay. Do not have confusion. Why I am putting phi of h as plus? I mean zeros. Okay. I mean phase as zeros, because they generally stable. Here A, B, C, D symbols mean I mean phases to be 0 or pi, 0 or pi, 0 or pi, 0 or pi, 0 comma pi, that is all. So, these are the E values. So, these 3 are called origin defining reflections, because I know the symbols of these 3 reflections to be plus 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 or phases to be 0 0 0. Now, with the knowledge of these limited reflections, let us say 5 plus 3 8 reflections, I am going to get the symbols or phase values for the remaining hundreds of reflections, that is called hand propagation. Now, so these 5 more reflections second bunch are chosen for origin fixing, and the signs are initially assigned as A, B, C, D, E. Each one of the signs can be plus or minus, and now you are using sign propagation or hand propagation. These have been done manually before the advent of computers, and these people struggled with this in getting this propagation. Sometimes they may get wrong result in between. I tell you how. Again they have to go back to start and again do the hand propagation. These are some complications. This is also called symbolic addition procedure, because in non-center symmetric you are just adding phases to get the phase of the new reflection. Usually for the reflections to be chosen for your propagation, this will have the mod yields normally such a factor greater than 2.0, so that the estimate becomes probabilistically reliable. That is it. Now, we have a table. This tells you that this is a centrosymmetric structure. N atoms are positioned x, y, z. Out of total n by 2 will be at x, y, z, and other 2 will be minus x, minus y, minus z. Okay. So, this already we have seen. In centrosymmetric case, if the sign of H reflection is positive, which means that the phase of the reflection H is 0, and if it is negative, which means that phase of the reflection is pi. Okay. So, we already seen in the phase about the lectures on phases direct method, this centrosymmetric case has two choices, 0 or pi. So, because of that, structure factor as usually defined as complex nature, f h equal to mod f h e power I phi h. Now, this e power I phi h can have only two choices, plus or minus. Therefore, f of h becomes plus f h or minus f h. Plus mod f h corresponding to phi h equal to 0, and minus mod f h corresponding to phi h equal to pi. Okay. In general, phi of h reflection will be minus of phi of h bar reflection, but since your phases is 0 or pi, minus 0 is same as 0 and minus pi is same as pi, because with any angle you can add 2 pi, minus pi plus 2 pi becomes pi. Okay. So, this is the condition. Now, we have structure factor values. A mod of f h k will be equal to f of h bar k bar L bar. Then this for all reflection, the parameter epsilon should be equal to 1, because this is used in the calculation of E values. Now, this is again to overcome confusion, I reproduce the table. Let us consider a reflection 2 1 4, right. Another reflection 0 2 bar 10 bar, some reflections are there. Okay. Now, when you add h plus k, what I mean is your h k L, you add this 2 plus 0 2, 1 plus is like minus 2, 1 plus minus 2 is minus 1, that is 1 bar, 4 plus minus 10 is minus 6, that is 6 bar. Clear? This is how you add the reflection. H is added with k to get h plus k. Of course, remember each is a 3-dimensional reflection, bar means minus. Clear? Now, see here, this 2 1 4 is in the list, it is plus, okay, right. Then 0 2 bar 10 bar, it is also A. So, in centrosymmetric, when you invert all reflection 0 2 10 2 0 2 bar 10 bar, your A will remain A, because your A is what, 0 or pi, right. If it is minus A, it becomes minus 0 same as 0, minus pi same as pi. Therefore, there will not be any change. So, now we get an answer, sin of h multiplied by sin of k should be equal to sin of h plus k. Your aim must be to find sin of h plus k. How to find h plus k? You just added, fine. Now, only unknown is what is sin of h plus k, is nothing but sin of h multiplied by sin of k as per Sayer's equation. So, sin of h is nothing but plus sin of k is nothing but A. Therefore, sin of this reflection is A, right. So, you have found sin of this reflection is A. So, this is called a, these are parent reflection, this is called a daughter reflection. This sign or phase of the reflection was previously unknown. By using this origin defining reflections and Sayer's equation, I have found the sign of a new reflection 2 1 bar 6 bar as A. Clear? Now, we have 2 1 4, another reflection 0 2 bar 10 bar. Okay. Now, what is H plus K? 2 plus 0 2, 1 minus 2 minus 1, 4 minus 10 minus 6. Okay. So, this I already have seen, same thing I am explaining. So, 0 2 bar 10 bar is same as 0 2 10 because A. So, now we got this sign. Now, let us take second block 2 1 4 with 1 bar 1 7, right. Add this 2 minus 1 we get 1, 1 plus 1 2, 4 plus 7 11. So, this is one H reflection, K reflection, H plus K reflection. So, knowing the sign of 2 1 4 and sign of 1 bar 1 7 reflection, I can get the sign of 1 2 11. Okay. Now, let us see what is the sign of 1 bar 1 7. We have the reflection 1 bar 7 bar as plus. If you take inverse, that minus minus of everything, from this I get 1 bar 1 7, because it is plus, it is going to be plus also for inverse, that is what I told you. If a reflection has a sign or phase 0 or pi, sign plus or minus, inverse reflection will also give the same sign. Therefore, 1 bar 7 bar sign is the same as 1 bar 1 7, which is plus. Okay. 2 1 4 already we have plus. Therefore, the sign of this will be sign of this multiplied by this, I mean plus multiplied by plus plus. So, I have found another new reflection 1 to 11 and its sign is plus. See, I have found now two reflections, new reflections. One is this reflection. Now, I have found A, then plus. Now, after doing this full exercise, I can get the value of A, B, C, D, E symbols. Okay. A, suppose uniquely say A has to be plus, then wherever you get the answer of the daughter reflection A, you just change it to plus. I will show you towards the conclusion. Now, let us see this block 6 and 8. See here, by doing addition of different reflections, I get the daughter reflection to be same. See, 3 3 8 bar is a new reflection, and that is got in two different ways. From 3 5 2 and 0 2 bar 10, when I add, I get 3 3 8 bar, because 3 plus 0 3, 5 minus 2 3, 2 minus 10 minus 8. But here other pair, different pair, 2 plus 1 3, minus 1 4 3, minus 6 minus 2 minus 8. Clear? So, now knowing this and multiplying this symbol, I can get the sign of this. Knowing completely different reflection and their signs multiplying, I get this, but this has to be equal to this. Clear? This has to be equal to this. Now, we have three different ways of getting the same reflection 1 1 bar 1 1 3, right. So, 1 1 3 is obtained from different pairs 1 1 bar 7 bar 0 2 10, when you add 1 plus 0 1, minus 1 plus 2 1, minus 7 plus 10 3, 4 minus 3 1, 4 minus 3 1, minus 5 8 3, 2 minus 1 1, 3 minus 2 is 1, minus 9 plus 2 1 1 3. Now, what you have to get is every answer should be the same. Suppose in your course you get different values, then your entire process is wrong. You have to go back to the starting set and assign new symbols, then proceed. So, let us stop with this now. In the set 8, you see that 113 has been obtained in three different ways, but the answer you get for 113 has to be the same. If not, there is a problem in the propagation. You go back to the origin differing reflection and change the sign. Otherwise, you remove this 1 1 bar 7 bar and 0 2 10 reflection and put some other reflection. That is all. Thank you. We will continue later.